So here's our bell work. Nice, good 5 questions right here. And just in case you didn't know, this is what we call a protractor. We're not actually going to be using protractors today, but just so you understand, in 9th grade, you're going to be using these quite a bit. And this is kind of one way to read it. But you'll go into that in more detail next year. So really, our objective today is just to know when sides make a triangle. Some of the rest of the stuff that would have been on today's lesson is actually going to happen next year. But for now, we're just focusing on when sides make a triangle. You were supposed to cover this last year in 7th grade, but me and Mr. Fields asked the teachers, and no, they did not cover it because of the COVID thing. Okay, but take 30 seconds and copy this down, please. Now, just a little bit of background on today's lesson, or at least the first part of today's lesson, is when you look at a triangle, okay, so a triangle has 3 sides, of course, like these 3 right here. And yeah, we'll pretend like I'm supposed to close that one right here at the edge. But it's supposed to be a 3-sided figure that closes, and all the side lengths are straight sides, okay? So once they get curved, then it's a different type of shape, okay? But this is a triangle for us. But what we need to know about the 3 sides, okay, is what you would do is you take the longest side. So for me, I guess I'd say that this side right here is the longest side. And then you got the 2 other sides, which are not as long as the longest side. Just like we talked about with the Pythagorean theorem. I mean, with the right triangle, the longest side is called the hypotenuse. But as far as I remember, there's not really a technical name for the longest side. And if there is, I don't really care. So the longest side, though, of a triangle, it has to be bigger. Nope, I said that backwards. It has to be smaller than the other 2 sides together. Okay, and that's kind of the crucial point that we're trying to make with this. And that's pretty much the objective. If you can understand that, then you at least get this first part of the objective down. So the 2 short sides of a triangle need to be more than the longest side. Now, we say they have to be more than the longest side, which means they cannot be equal. It definitely cannot be shorter. And hopefully this kind of makes sense, because if we looked at an example where the two side lengths were the same, let's say they were the same, right? So the red side and then the green side, I'll just kind of emphasize this. If they were the same length, then you'd get 2 side lengths that are the same length as the purple one. And the moment that you start to angle this thing away from the purple line or even the red one, then the 2 lines come apart. But this does not close into a 3-sided figure like we see with regular triangles. Okay, so that's why this doesn't work when they're the same. If they were shorter, then what you'd end up with is, let's say, let me just kind of emphasize that they're shorter like this. And you can see that no matter how we try to angle these together, they have to connect at the edges, by the way. So yeah, we can never force these 2 to come together, but it's an open figure now, which is why it's also not a triangle. The 2 short sides have to add up to be more than the longest side. All right, so for this one, and they're kind of labeling the edges of the triangle for us. I mean, it'd be triangle ABC, but what we notice about this is that the 3 and the 3 are shorter than the 8 right there, right? Try to use green. So 3 and 3, when I combine those, I get 6. Well, 6 is not bigger than 8. So could you make a triangle out of this one? No, it's not a triangle. Okay? Now, just to emphasize this point, let's look at some other values, okay? Such as, I don't know, 13, 25, and 14, okay? Now, sometimes they'll do this. They'll say, hey, look, these 3 side lengths. Well, 13 and 25 is bigger than 14, but it's not in order. Remember, it's the longest side, right? So let's say the longest side is 25 here. The 2 short sides, 13 and 14. When you add these up together, 13 and 14. I'll show the math. What the heck? 13 plus 14. This is 27. And that is bigger than the longest side, 25. That's what we need. So yes, this one would make a triangle. Okay? That's all you got to do in order to figure out if three side lengths make a triangle. Add up the two short sides. If it's bigger than the longest side, then it is a triangle. And think about this too. If the 25 was 27, then it would be exactly equal, and it's still not a triangle, okay? But since it's less than, that's okay. So what has to be true about the two smaller sides of a triangle compared to the third side? Well, the sum of the lengths of the two small sides must be longer than the longest side. This is just a different way to say what we said before, but it's saying exactly the same thing. So another thing about triangles real quick. Okay, let's look at an obtuse triangle. It's a little bit different, right? Something like this. Okay. Now, just so you understand, usually when they label the corners right here, and there is a technical name for the corners which we need to know. These are what in fact I'll label these in red. These corners, they're called vertices. Vertices, like this, okay? Or a vertex. An individual one is a vertex, so there's individual and plural, right? Singular and plural. Now, when you label vertices, like we see here, you generally use capital letters. So I'll just choose one randomly, like T, and then E, then U, right? Okay? So, if you were to name this triangle, here's what you would do. You'd call it triangle. All right. And then you just name the three vertices right here. So that'd be angle, oh, there we go, triangle. That's very nice, okay? Also, this one's obtuse, not that we really care about that right now. But you need to understand that we use capital letters for these vertices because eventually we're going to start naming the angles. But this is how you would label a triangle. You wouldn't want the points in between on the lines. And something else about these is if you look at the line, the length of one of the sides of the triangle, this is what we call a line segment because it's just part of a line. Right? Remember, lines usually have the arrows at the edges of the lines to indicate they go forever. But since these ones do not, this is called a line segment. This one specifically would be line segment UE right here. And they usually put a line over that. It won't always, depending on the technology that's used. But yeah, line segment UE, that's how we would demonstrate that. What has to be true about the measures of the angles of a triangle? All right, if you look at the three angles of a triangle, you'll find that they always have to add up to 180 degrees. Well, what do we mean by degrees? Well, if you look at two lines like this with some kind of vertex like this, and another one coming out of that vertex right here. An angle is essentially the space created between the two lines right here in relationship to that vertex, okay? So we label these in what we call degrees, just like you would with temperature. Like this one, maybe it's, 20 degrees, something like this. And the farther apart the lines become, so if I were to take this line and expand it, the bigger the number gets. The closer these two lines get together, the smaller the number gets. Again, it would create a smaller amount of space, so the smaller number, if you expanded them, then or made them farther apart, then it would make that number bigger. So that means that for any triangle, doesn't matter if it's obtuse, so an obtuse triangle has one angle that's bigger than 90 degrees. That's kind of vocabulary that we expect you to be familiar with, but also not so much right now, okay? It was kind of a big deal in 7th grade, but this angle right here would say is bigger than 90 degrees. But all three of these angles add up to 180 degrees. The red one, the purple one, and the green one. It wouldn't matter if it was acute, where all three angles are less than 90 degrees. And maybe you can draw better triangles than I can, but I don't really care. Because those three angles would add up to 180 degrees. And even for right triangles, which we've seen with the Pythagorean theorem, I mean, you got the one that's 90 degrees right here. But the other two angles, together with that orange one for the right triangle, would still add up to 180 degrees. And we have vocabulary for those relationships, which we will get into later. So look at these examples and non-examples for these vocabulary. This one specifically is for complementary angles, okay? So it would say, hey, look, this one right here, complementary. This one, complementary. This one, not so much. Same with this one, not so much. Okay, not complementary. Well, now you may look at these for a while and think to yourself, what the crap am I looking at? And these are angles. And what do you notice about these two? Well, I don't know what you'd notice, but here's what you're supposed to notice in any case. The two angles add up to 90 degrees. Same with these two, 47 and 43. Now you see that these two are kind of together. They share this, we call that a ray right there. Whereas these two are not sharing the same line, which means that it doesn't matter where the two angles are. Like you could say, well, hey, look, we got this angle over here, and we'll say it's 40 degrees, and you could have this angle over here, and it's 50 degrees, and these two angles would be considered complementary, okay? Doesn't matter where they are. If they add up to 90 degrees, that's all that matters, and so that is what we would say is true about complementary angles. It's not, and we're just showing two angles, but it could be more, so it's two or more angles that add up to 90 degrees. There you go. So give examples then. Yeah, that's not too bad. Give examples of two complementary angles, okay? Well, that would be something like we just saw where there with 40 degrees plus 50 degrees, that would be 90 degrees. You could cut it in half and say 45 degrees plus 45 degrees, that's complementary. But again, it could be more than two angles as well. You could say, well, 30 degrees plus 30 degrees plus 30 degrees. And yeah, that's still complementary because now it's more than two angles, but it still adds up. All three add up together to be 90 degrees. That's the main thing with complementary angles. So what about these examples? Again, we got some examples, some non-examples, but this time we're looking at what the heck? There we go, supplementary angles this time. Well, we see that this first one, that's supplementary. Second one, supplementary. This one, not supplementary. Same with this one, okay? These are not supplementary, the last two, but the first two are supplementary. And again, you'd be looking at the angles because, well, it's labeled in angles. And you'd notice, hopefully, if you looked at these closely, that if you added the two angles, at least that are given for this one, they add up to now 180 degrees, right? 85 plus 95, 180. Same with 75 plus 105, boom, 180 degrees. Now again, this one shares a ray, this one does not. That's okay, it doesn't really matter where they are. If we're asking for supplementariness, then the two or more angles just have to add up to 180 degrees, that's all. Okay, so supplementary is two or more angles that add up to 180 degrees, that's all, right? So give examples of two supplementary angles. Of course, a common set is where you just cut the 180 in half and you'd say, well, that'd be 90 degrees plus 90 degrees, boom, okay? But again, it could be more than two angles at a time. You could say, well, 45 degrees plus 45 degrees, oops, plus 45 degrees. Well, that's not still 180 yet. Let's add another one. We divided it by 4, that's all, okay? And it wouldn't matter as long as the two angles add up to 180, they don't have to be the same like we saw there. You could say, well, what about 100 degrees and 80 degrees? Yep, they're supplementary. So supplementary is 180 degrees. Now, if I haven't said this before, as you should know, anyways, is math people are all about looking smarter than we are, right? So not only is there this vocabulary for making math people look smart, like if you went to people and started talking about supplementary angles, they may punch you because they think you're a nerd. But in any case, once people start to figure out supplementary, then we change the vocabulary. This is also known, supplementary angles add up to what we would call a straight angle. A straight angle. Oh, I use this symbol right here. This is the symbol for angle, and that way you don't have to actually write the word for angle all the time. So that's a straight angle. But also, it is possible, especially when you have two, specifically, we also call it a linear pair. See how we're using 3 different words for pretty much the same thing on this? Yeah. That's just to trick people into thinking that we're actually smarter than we are. And people do think we're very smart, super smart, in fact. Even though sometimes, well, we not actually, okay? So, this is the same vocabulary for exactly the same thing. 180 degree, again, 2 or more angles, but linear, straight angle, sometimes just one angle right there. So that's kind of how I remember it. Supplementary means a straight angle, which means that if you took supplementary angles, let's look at an example like, see this line right here? If you looked at this red angle and this purple angle, we would say they're supplementary, or that it's a straight angle because it creates this straight line. So that's kind of how I remember. S for straight is 180. S for supplementary, I don't know. Sometimes it helps, sometimes it doesn't. But that's how I think about it. What does it mean for 2 angles to be adjacent? Well, adjacent angles, they need to share either a line or a ray or a line segment, something like that. So let's look at, this is a line right here. We'll put it on black. We'll pretend like I drew a straight line, by the way. And we'll put the vertex right here with some other ray like this one. There's a ray. You can make it a line segment if you'd like. But let's say this angle right here and this angle right here. Now, just based on what we barely learned, we would say these are supplementary. But not only supplementary, these 2 angles are right next to each other, and that's what adjacent means. The 2 angles they just need to be right next to each other, okay? So that red and purple angle are what we call adjacent. Sometimes what you'll have is maybe a diagram like this one where it's just an angle that's maybe been split like this. Well, this green angle and this orange one, they are still adjacent, okay, because they're just right next to each other. Again, that's all they need to be, but they need to share a line, a ray, a line segment, something like that together, okay? They have to be right next to each other, and this will be important because we have another vocabulary word for ones that are kind of opposite to each other at an intersection or vertex. So this is kind of a nerdy way to say what we just barely said. Again, I kind of like the 2 angles that are right next to each other with an emphasis on that they share some kind of ray or line. That's kind of the important part right here, okay? But this is the nerdy way to say 2 angles that share a ray or line and a point through that ray or line. Boom. Okay, so the point that it's talking about is just the intersection, okay? So, for example, sometimes when people talk about directions, they'll say this grocery store is adjacent to this gas station or something like that. It just means they're right next to each other, but across the street, essentially, from each other as well, okay? Draw a triangle on scratch. We're not gonna do this activity. You're welcome to do it at home. Your parents may worry about you if you do, though, because I mean, how many people actually go home and work with triangles? I don't know. However, some of you guys may. I don't know, but we're just gonna do this on this one with this triangle. But you could technically do it with any triangle if you're really curious about that. Go home and do it, and you'll see that it works. Okay, but remember what we said in the first part of this lesson is that, or at least one of the first parts, is that the 3 angles of a triangle need to add up to 180 degrees, right? Well, 180 degrees makes a straight line, just as we've seen. So we're going to see if I don't do this perfectly all the time. I'll try to draw the lines or the angles exactly like we see them. So there's angle 1, right? And I can take angle 1, maybe. And I can set it aside right here, right? And then I can take, let's go to angle 2 now. I'm going to kind of copy this one so that I can move it as well. There we go. There's angle 2. And I can also take angle 3 here. I tried to draw that pretty good. I'll try again. There we go. I think that's better. Angle 3. Now let's take angle 3 and also separate it from the triangle like this. Okay, so there's our 3 angles. Green is angle 1, blue is angle 2, and then the orange there is angle 3. Now, we probably noticed from that my drawing sucked, but when I combine these 3 angles, as you see here, and we can even label them, there's angle 1, there's angle 2, and there's angle 3 right there. But what's supposed to happen, if you draw this a little bit better than I did, is it will create a straight line right here, okay? Well, what do we know about straight lines? Is that it's a straight angle. Or what we call supplementary angles. Okay? And what does supplementary angles mean? It means that they add up to 180 degrees, just as straight angles do. Okay? So you could say that this is linear triple if you would like, but I don't think we need to go that far. But you'll find that this is true for any triangle. This one we would say is an acute triangle. It would work for right triangles. It would work for obtuse triangles. Doesn't matter what type of triangle it is. It will always work. The three angles add up to exactly 180 degrees. Yeah, we can put that in there. There we go. That's better. Now, there's a relationship then between what we call exterior angles and some of the interior angles here, okay? So the inside angles, such as we see in green, orange, and blue right there, these are what we call interior to the triangle because they're on the inside. If they're on the outside, we call them exterior angles. But if we were to work with this a little bit more, you'd see this angle. I'm gonna show it as angle 4. It's exactly the same as angles 1 and 3 together, okay? And this is what we call remote interior angles. Let's fill by the purple one. Okay, so this means that what we would call angle 1 and also angle 3, if you were to add these two together, whatever they are, you'll always get this exterior angle, angle 4. Why is that? Why does that work? Because this full angle right here is a supplementary relationship. There's straight angles. It makes a straight angle. And also, all three angles on the inside make a straight angle. So that's why this angle is the sum of these two. Now, you don't have to understand that, except that we're just going to be using it to solve some problems here in the future. So naming angles, so we looked at naming triangles in this lesson already, but naming angles, here's what happens, okay? So like a triangle right here. Let's look at a triangle here. We'll say we got vertexes A, B, and C, right? Now, if I wanted to name this angle, here's what we do not want you to do, although you'll see it in the assignment because this thing jerks, okay? But some people would say this is angle A. Now, I mean, it's kind of true because we marked it. However, it's not necessarily technically what we want on this, okay? What you need to use is 3 letters to name an angle, particularly in the order that you would go in to create the angle. So for me, I'd say start at B, then go to A. So that's B, then A, and then A to C. See that? So that'd be angle BAC. And you could say, well, I don't want to do it that direction. I want to do the other direction. That's okay. You can call it CAB if you'd like. Okay? These two are the exact same angles. It is okay to label them, so you could also call it angle 1 if you'd like. But we would definitely not want to call it angle A, okay? Now later on, you'll get into more technicalities with the naming of angles, but for now, this will do for us, okay? Now that's for a triangle, but it's the same thing with angles generally. So sometimes they don't connect to make a triangle, right? So you could say, hey, here's an angle right here. And we'll call the vertex, I don't know, G, I guess. Now, again, you would not label this angle right here. You would not say, this is angle G. Okay, you would not want to do that. But in order to actually label it correctly, you would want 3 points. Only one of them is a vertex. The other two are just on the line. So G, H, and I don't know. So that angle would be angle HGI. Or if you'd like to, IGH. Notice that the letter of the vertex is in the middle for where we want it to be. That's why we don't call it angle G, one of the reasons. But yeah, remember, you're just following the letters on the lines, HGI or IGH. So when we see a diagram like this, now we know what they're talking about. Let's start with vertical angles. Okay, so this one right here wants to know identify or describe how to identify vertical angles, and then we'll also describe what's true about the measures of vertical angles. Now, something else you need to understand about this is when you see an M in front of the angle symbol, remember this is our angle symbol, usually I put a little line right there. This M, right here, we'll do it in a different color. This M stands for the measure. Now, measure is a long word, that's why we don't want to write it all the time, so we just use M. M, measure of angle ABC. Now, we've seen the letter M used in a different setting. That was for slope-intercept form. This is not slope-intercept form. We're looking at angles now, so it's the measure of angle ABC. Yeah, remember, that's how we make ourselves look smarter than we are. In fact, that's sometimes how we make math more complicated than it needs to be as well. This is one of the ways we do it. We use the same letters for different things, or we change the wording on stuff, which is something you should understand, because if you think only math people do that to make us look smarter than we are, then you have been fooled. So, vertical angles though, let's see here, what do we got? ABG and CBE are vertical angles. So ABG, let's find ABG, that's this angle. And angle CBE, so that's this one right here. That's the full angle right there. It says these are vertical. Okay, that's interesting. They're not adjacent. I'd say these are opposite of each other at the same intersection, and that works. Well, what about ABC and EBG? This says they are vertical angles, right? So ABC, that's this angle. And then angle EBG, that's this one. They're vertical as well. And again, we should be noticing here that they're through the vertex, okay? Well, that is how you identify vertical angles. And let's look at a non-example such as this next one, okay? So ABG, this angle is not vertical with angle CBD, this one. Okay, now it's close. These two angles in green are not vertical. So why are they not vertical? Because they're still through the vertex, right? It's true, but not only do vertical angles have to be through the vertex, they also have to be exactly the same size. Okay? So that's what I'm going to put over down here. Describe how to identify vertical angles. Angles that are opposite of each other through the vertex or intersection. Yeah, and that's why I drew those lines, the one in red and purple there, because they're through the vertex. But they also have to be the same measure, I guess. Now, the same measure stuff, there's another way to describe this in math, just like you'd expect. So yeah, what's true about the measures? Right here, let's answer this one real quick. They are the same. So, when we want to say something is the same in math, of course, we want to make it more complicated than it needs to be, and this is what we do, okay? I'll do this in the bottom left here. If I wanted to say that something in math is the same, especially with measurements, the same, we say that it's congruent, because congruent sounds more, well, it makes us sound smarter than we are. Congruent. And there's actually a symbol for congruent, so we don't have to write the word all the time. See how math kind of becomes kind of like hieroglyphics? Well, this is the symbol for congruence. And it's an equal sign with, I don't know, I think it's called an NEA symbol, I don't know. An approximation symbol above it, something like that, okay? So if we wanted to say that angles are the same, we can say that they're congruent, and we could use the symbol between them, okay? So on this example, where we have vertical angles, such as this first one that we saw, angle ABG, and also angle CBE, they are vertical, but if I wanted to demonstrate that they're congruent, I could put a congruent symbol between them. And yes, I've drawn better congruent symbols, but that will work. How do we identify a linear pair? Well, linear we should already know. We've heard that word before. We had a whole unit and a half on linearity, which just means to create a straight line. So straight lines indicate that we're looking at straight angles or supplementary relationships. So on this first example here, it says that angle ABD and angle DBE are a linear pair. So let's see, ABD, that's this angle right here. This one. And then angle DBE, right? So DBE right there creates this angle. Well, yeah, what do we get when we combine these two angles together? Well, you get a straight line right here. Okay? So linear pairs means that we have a supplementary relationship or that the angles add up to 180 degrees. So we'll write that in here. What is true about the measures of the angles of that form of linear pair? It's the same thing that we just wrote right there. That works. Yeah, this is another way to say it. They combine to make a straight line. That's good. Okay. All right. We're just going to do number 8 on this one, and then we'll do number 9 and 10. We're going to do them separately because I need the space on this. Okay. So it says angle A and B. Remember, that's an inappropriate way to label your angles, but here it is, okay? And also remember the M in front of the angle measure says angle symbols means that we're measuring the angle. Measure of angle A is this expression. Measure of angle B is this expression. But back here it says that they are vertical angles. And we just learned that vertical angles are congruent. So there's our congruent symbol, okay, which we need to know, which means they are the same and the same exact measurement. So this means that if I wanted to solve this, I would have to take the measure of angle A, which all I know now is 3x plus 2, and the measurement of angle B, which is 5x minus 6, and I would have to make these equal. Now it does say find the measure of angle A, which we will do, but we don't know the measure of angle A until we can solve the value of x. So I'm going to use principles of equality. I'm not going to do this too much in the future, but right now I'm going to do this in 2 steps. Okay, so I'm going to put my x's on the left, numbers on the right. I do not see a need for distribution or combining like terms, so I'm going to go straight into my principles of equality. Putting the x on the left, I would have to zero out that plus 2, the positive 2, by subtracting 2. But the principles of equality say if you do it to one side, you must do it to the other side. So that does work, though. We're going to drop the 3x. 2 minus 2, that's going to be 0. This will equal, we'll drop the 5x. And then we got negative 6 minus 2. Remember, the operation will determine the sign of the term. So negative 6 minus 2 is negative 8 right there. But now the 5x is on the wrong side of the equal sign as well, so we're going to have to zero it out. So subtract 5x, but if you do it to one side, you must do it to the other side as well. So there's a subtract 5x. And so we got positive 3x minus 5x, that'd be negative 2x's, which now equals 5x minus 5x zeroes out, and then we're going to drop the negative 8 there. Just divide both sides by the coefficient, which is the negative 2 to make that a phantom 1. Phantom 1x now equals negative 8 divided by negative 2 is 4. Now we feel pretty good about that because it was a lot of work. However, it did not ask us to solve for x. We just had to do it in order to find the measure of angle A. So now I'm going to go to the measure of angle A, which I know is, take that back. Measure of angle A is 3x plus 2. So we're going to write this in as 3x plus 2. But I know that x is 4 now, right? Just like we found there in green. So x is now 4. And then I solve this. 3 times 4 is 12 plus 2. 12 plus 2 is 14. Now, usually would say that the measure of angle A equals 14. It's not 14 though, it's 14 degrees. Make sure you label that, otherwise you may lose some points. Of course, on the assignment, I think you just got to put the 14 in there, but if you're doing this by hand, you'd have to label it. So that brings us back to the old school, right, where we were solving equations from the beginning of the year. Those were some, good, better times, I guess. I don't know. But hopefully hopefully remember that stuff because you're going to see a lot of it in the assignment today. All right, so number 9, angle C and angle D are complementary. Angle C is 6x plus 10, and angle D is 3x plus 26. What is the measure of angle C and the measure of angle D? So we got to do each of these separately. But again, we see here that the relationship is complementary. Complementary, hopefully you remember this already. If not, you can look at the poster. But it's 90 degrees. So that means if you took the measure of angle C, which is 6x plus 10, and the measure of angle D, which is 3x plus 26, since they are complementary, you would add these two together and you should get 90 degrees. Okay, so this sets up an equation for us to solve, and solve it we will. So, keep that 90 in there. Let's go and solve it. First thing I would do on this, I would look for a distribution, but I don't see any. So then I would go straight into combining like terms. With the 6x's and the 3x's, that would combine to be 9x's. The 10 and the 26 would combine to be 36 positive. And this equals the 90. Okay, so we just simplified the expression. Now, to isolate the x's, I'll zero out the 36 by subtracting it from itself. But if I do that, I got to do it the other side as well. So I'm dropping my 9x. 36 minus 36, that zeroes out just like we want. And this now equals 90 minus 36 would be 44? No, 54. There we go. 54, but we don't want 9x's, we just want 1x's, so divide by the coefficient 9, which now makes this x equals 54 divided by 9 is 6. Now again, that should feel pretty good. I mean, it was some work, but it's not the final answer that we want. We just solve for x. Sometimes it will just want us to solve for x, but last thing we need to do is actually solve for the measurement of these two angles. So, angle C here is 6x plus 10. And we just found that x is 6. So, I replace the x with 6, and then I solve. You can use a calculator to do it, but this isn't too bad, so I can do it by hand. 6 times 6 is 36, plus the 10. 36 plus 10, boom, 46. Now that's in degrees, that's the measure of angle C right there. That's our first answer. Then we have the measure of angle D, which is 3x plus 26. And we know that x is 6, so we replace x with 6. And solve. So 3 times 6 is 18, plus the 26 there. Combine these two, and we should get 44 degrees. That's the measure of angle D. Well, last thing we should do on this is just check. Just check to make sure that we got the correct answer. So if we took these two angles, right? Angle C, which is 46 degrees, and angle D, which is 44 degrees. If we were to add these, because they're complementary, we should get 90 degrees. And yeah, we do. That's 90 degrees. So it just checks off. Now we know for sure that these two answers are correct. So that brings us to number 10. Angle F and angle E are supplementary. And it's important to remember that supplementary indicates that we're looking at straight angles, or would create a straight angle, so that's 180 degrees right there. And they're also adjacent, which means that, I mean, that doesn't really matter so much as the supplementariness, but they'd be right next to each other if we were to draw a diagram of this, okay? So we need to figure out the measure of angle F and the measure of angle E. Wait till this one's done, please. Okay. So, the two angles, right? They're supplementary, so we'd have to add them together to get 180 degrees. So we know angle F is 2x plus 20. And angle E is 3x plus 25. So if I were to add these together, I would need to get that 180 degrees right there, okay? So this just becomes an equation that we need to solve. So let's solve it. Combining like terms with the x's first, 2x's and 3x's would be 5x's. And then 20 and 25, that'd be a positive 45 right there. This will equal 180 degrees. So just simplifying that first part. Now to isolate the x's, I would subtract 45 from both sides. To zero out the 45 there in red. we'll drop the 5x, which now equals 180 minus 45 is 135 right there. And then the last thing to solve for x is divide by the coefficient 5 to make the coefficient of phantom 1. So phantom 1x equals, looks like 27. But again, that's not the actual answer. We want to find the measure of angle F and the measure of angle E. So let's go ahead and do that. We know that the measure of angle F is 2x plus 20, but we just found that x is 27. So I replace the x with 27 and I solve. So I'd say 2 times 27, that'd be 54, plus the 20 there. And now when I combine these, it looks like I get 74. So it looks like the measure of angle F is 74 degrees. We'll still check this later, but for now this is good. And then the measure of angle E is 3x plus 25. We know that x is 27. So I replace x with 27 and I solve. 3 times 27, 60, 81 plus 25. Now combine these. 81 plus 25 is 106. So this would be the measure of angle E right there. Degrees, don't forget the degrees label. And can we check this? Yes, we can. I'm just going to take the two angles, 74 and 106, and I'm going to add these together. And what should I get? 180. 4 plus 6 is 10. 7 plus 1 is 8. 180. Boom, it checks off. So now we know that that's correct. Two angles of a triangle measure 38 degrees and 101 degrees. What is the measure of the third angle? Okay, so this is what we're going to do if you need to solve for the third angle of a triangle. We'll just kind of draw this out. Doesn't really matter what it looks like. Something like this. So this one right here is the 101 degrees. It's got to be bigger. And then, I don't know, we'll call this one the 38 degrees. So we're solving for this angle here that I've drawn in green. Not that it has to be that way, but we know that the three angles have to add up to 180 degrees, right? Now to solve for a missing angle that way, which we should know by now, you're going to take the 3 that should add up to 180 and just subtract the 2 that you know. So we're going to subtract 38 from the 180 while also subtracting 101. Now, am I going to do this by hand? I am not. I'm just going to put this into the calculator and see what I get. And when I do, I get 41 degrees. Okay. I did that in the wrong colors. It should have been red right there. This one will be green. So the measure of the third angle, 41 degrees. So number 12, here's our alternate interior angles thing. So this angle here, 25 degrees, and this one, x plus 15, it has to equal this one on the outside right here, okay? Because this angle doesn't matter because these two are the same as the green one right there. So we're going to list them. We got the 25 in red, we got the x plus 15 in purple, and then the 3x plus 10, minus 10 in green right there. But if you take the purple and the red one and add them together, it should equal the green one right here, okay? So this becomes an equation for us to solve as well. And to solve it, I'd combine my like terms, the 25 and 15, which is 40. So now I got x plus 40 equals 3x minus 10. And I'm going to put my x's on the left and the numbers on the right. Not that you have to, but that's what I'm going to do. So the plus 40, I'm going to subtract it from itself. But if I do it to one side, I got to do the other side. I'm going to do the 2 steps in one here. I'm going to subtract the 3x and zero it out right now as well. So that's really 1x minus 3x there. The 40 minus 40 zeros out. The 3x minus 3x zeros out. And then we got 1x minus 3x, which is negative 2x. This equals negative 10 minus 40, which is negative 50. Last thing here is just divide both sides by negative 2. So now x equals 25. That's all it wanted from us, is to solve for the value of x. That does not mean that x is 25 degrees, it's just 25. And then that would make it a true statement. Of course, you can check these, right? You could say, well, 25 plus 15, that's 40, plus 25 is 65. 25 times 3 is 75, minus 10 is 65. So they match. All right, let's find the value of x on this one. This angle relationship is vertical because they're through this vertex right here. Okay, so they're opposite each other through the vertex. And we just got to find the value of x. Now, since they are vertical of each other, that means that they are also equal. So the two angles, 3x plus 45, and the other angle, 6x plus 18, they are equal. So let's use our principles of equality to solve this. No need for distribution, no need for combining like terms. You put my x's on the left side of the equal sign, numbers on the right side of the equal sign. So I'd have to zero out the 45 probably first. But I can do it simultaneously with subtracting 6x to zero that out as well, okay? So that will zero out these two terms. 3x minus 6x is negative 3x. Equals 18 minus 45. Let's see, 30, 27, negative 27. Then divide both sides by the coefficient, negative 3. And we get x equals 9. That's positive 9, by the way, and we can check again. 3 times 9 is 27. Plus 45, 27, 45, 50, 60, 72, looks like. And then 6 times 9 is a 54 plus 18, yeah, 72. So that works. Then number 14, draw a linear pair. So I would start with a straight line like this one. Well, it's supposed to be straight. And then I would just draw a vertex anywhere, doesn't matter where, and then just any line coming out of it, like this one. Then I would show this angle here in purple and this angle in green. Those two are a linear pair because together they make this line right here, if I had drawn it better. So there we go, there's those three problems. And here's our objective. I can name and I guess find or solve angle relationships. That's good. So for the two lessons that are in this unit, this is one of them. Next time, we'll be looking at different types of angle relationships, but this is all we got for now.